Part B. Part B asks us, what is the velocity when the ball is 35 meters above the ground? Okay, so the first thing we have to do is we have to figure out when it's 35 meters above the ground. So we know this max height here is 44.1. And so somewhere around here is 35 meters. So we want to know what's the velocity when the ball is at those positions. There's actually two of them. So in order to do that, we first have to figure out the times this occurs. So there's two little times there that we have to figure out. And we're going to take our position function, s of t, which is a negative 4.9 t squared plus 29.4 t. And we're going to set this equal to 35. Okay, so for in this problem we do have a quadratic. And so we have a negative 4.9 t squared plus 29.4 t minus 35 equals 0. And now we have to solve for that. Now usually when we're doing these problems that include the free falling problems, the numbers are such that you're never going to be able to factor it. We basically have to go straight to the quadratic formula. So the quadratic formula, t equals, and remember it's a negative b, so we have a negative 29.4 plus or minus the square root of b squared, so we have 29.4 squared, minus 4, a is a negative 4.9, and c is a negative 35. All over 2 times a negative 4.9. Alright, so I'm going to simplify it just a little bit. So we get a negative 29.4 plus or minus the square root of, okay, so we need our calculator again. So for this one, I'm going to do 29.4, and I'm going to square that. And then we're going to subtract the quantity 4 times a negative 4.9 times a negative 35. So this ends up being 178.36 all over 2 times a negative 4.9, which is a negative 9.8. Alright, so then it makes it easier to do our two choices. So t is approximately going to be, and we have to do both of the choices, we have a negative 29.4 plus the square root of 178.36, enter, divided by a negative 9.8. And that gives us 1.637. Right, that's seconds. And then the other one's going to be a negative 29.4 minus the square root of 178.36. And we'll divide that by a negative 9.8. And we get 4.363 seconds. Alright, so those are our two times. So going back up here, this would be about 1.6 seconds, and this is 3.4 seconds. And so the ball travels up, and it gets to 35 meters at 1.6 seconds, goes to its max at 3 seconds, and then it comes back down and hits 35 meters at 3.4 seconds. And we want to know what the velocity is at those 2 times. So now we need to calculate that. So v of 1.637, see, our velocity function was a negative 9.8 t plus 29.4. So it's a negative 9.8 times 1.637 plus 29.4. And that equals, so let's get that. Let's see, a negative 9.8 times 1.637 plus 29.4. And we get 13.36 meters per second. And this one is going to be the velocity at 4.363. It's going to be a negative 9.8 times 4.363 plus 29.4. So let's do that one. Negative 9.8 times 4.363 plus 29.4. That's a negative 13.36 meters per second. Okay, so here are the 2 answers. And in this case it makes sense, the ball comes up, and when it gets to 35 meters it's going positive 13.36 seconds because it's going up, and then it reaches its max height. Then it starts going to negative velocity, and so when we get to 35 meters again, it's going to negative 13.36 meters per second. And so its velocity, now remember, velocity has direction, so there is a positive velocity and a negative velocity. And in this particular problem, there is a lot of symmetry, because parabolas do have symmetry, and because we are assuming it's going from the ground up, there's going to be answers that look similar. Of course, later on we're going to have it so that so don't count on that every time. Later on we're going to have it where the initial position isn't at 0, and then all that symmetry goes away. So please don't come to me and say, well, because this was positive 13.36, I'll just write negative 13.36. You still have to go through the math. Okay, part C. When does the ball hit the ground? All right, so it started from the ground, goes up, hits the ground, and so it's going to hit the ground when the velocity is, not the velocity, when the position is 0. I think I can get this in here. Part C. We're going to take our position function, s of t, which is a negative 4.9 t squared plus 29.4 t, and we're going to set that equal to 0. And then we have to solve this. And again, it's a quadratic, but this is a much easier quadratic than we had up here, because this quadratic we don't have a c term, so we'll just factor out a t, factor out a common factor. So we have a negative 4.9 t squared, no, not t squared, just t, plus 29.4. So then we get t equals 0, and a negative 4.9 t plus 29.4 to equal 0. Okay, now t equals 0, that's one of our answers, which makes sense. We started off at 0. Let's get this other answer here. So we have a negative 4.9 t equals a negative 29.4. And so we're going to end up with t equals 0 and t equals, I'm going to calculate that. So we have 29.4 divided by 4.9 gives us 6 seconds. And then in this case, we just have to think about, well, what is the question asking? It's not asking when the thing is thrown up, it asks when it lands, so it must be this 6 seconds. Good. So one other thing I want to discuss is about the domain of our physical models. And we discussed this in pre-calculus, and we'll discuss it again in this class. But notice that this equation here that models our the path of this ball is a parabola that's that's downward facing. Now, according to this parabola, this thing keeps on going. You think about it. So what if I asked you, well, what's the position at 7 seconds? I mean, according to this equation, you can do that. So we could put a negative 4.9 times 7 squared. And then we're going to add 29.4 times 7, which gives us a negative 34.3 meters. Now, of course, that doesn't make any sense because a negative 34.3 would be under the ground. So we always have to remember that when we're using a math equation to model something in real life, that pretty much always there is some form of a domain restriction. In this case, this equation here is only applicable from 0 to 6 seconds. That's it. So always keep that in mind when you are doing these word problems, whether it's in this class or the AP exam or even a science class, that even though the equation says you can do something, it doesn't mean that it can actually happen. And so in this case, once we get to 6 seconds, this equation no longer applies. Actually, the position function would then just be 0 because it stopped. And then you'd have to have a different position function for what happens next. So here's a good problem with a free-falling body problem. We threw a ball up in the air, it gets a maximum height, comes back down, and we were able to find some information based on an equation that we created for the position.